Welcome to differential equations. Differential equations is one of the most powerful tools that we have for modeling and understanding the physical world. And in this video, I'm going to give you an introduction to the big ideas of differential equations. So, what is a differential equation? When trying to model the world, one of the things that we notice is that things change. Different objects move around, fluid flows, electric fields and magnetic fields, they change, stock prices go up and down. The world is changing. And we have seen a little bit of how to address, how to get our handle on a changing world in calculus. We've seen, for example, that if you start with some function like the function y of t, then you can compute the rate of change of that function or the derivative of that function y prime of t. Which was great, and maybe that would be helpful for modeling all these changing things in the world, except where did the original functions come from? As in, if you give me a function, okay, then I could differentiate and get its rate of change. I could differentiate twice if I wanted to. And one common way that they come from is called differential equations, and it's sort of working this process in reverse. Now, the big idea is that often, when we're trying to mathematically model a situation, we know more about how something is changing than being able to exactly describe the state of the object at every point in time. For example, consider a bank account. We often are told right up front what the rate of change of a bank account is. That will be our interest rate. So consider this equation that might model the scenario. The derivative of y is 0.03 times y. Y here is going to represent the amount of money in our bank account at time t, and we typically in differential equations do use y for our dependent variable. And what is happening is that this is the bank account with an interest rate of 3%. The fancy terminology is called 3% compounded continuously. And what that means is whatever amount of money that I have at a given point in time y, the rate of change of increase is 0.03, or in other words, 3% times that amount of money. If you have more money than I do, then the rate of change of your bank account is going to be higher than mine because it's always going to be the 3% of what you have. And so this is a differential equation. A differential equation is just an equation that has derivatives in it. So what can we do with this? Well, I want to notice that this equation actually has a solution. You can try it out. If you set that y of t is e to the 0.03t, it just works. I mean, plug it into both sides. If you plug it into the left, the derivative of e to the 0.03t is, well, 0.03 times e to the 0.03t. It's the same thing on both sides. So this function, e to the 0.03t, we say is a solution to that differential equation. You might have asked, how did I know that that was it? How are we going to come up with solutions to differential equations? And we'll talk a lot about that more coming up in future videos. Right now, I just want to say, given this function that I've just thrown at you, well, yes, indeed, it is a solution to that differential equation. And this kind of exponential growth, well, it works for bank accounts, but it also works for things like a pandemic. When we were having an exponential growth of a pandemic, it was the same thing. The rate of change of infections was some constant times the number of people who already had the infection. Similarly, the rate of change of some bacteria growing in a petri dish might be a constant multiple of the population. In all these examples, differential equation was relevant because we could say something about the rate of change. We could model it by making a claim about the rate of change, that the rate of change was proportional to the original values y. Now, I can go even further than this because, well, e to the 0.03t is a solution, but notice that 17 times e to the 0.03t is also a solution. I can plug it into both sides and I get that they are equal. And in fact, the 17 was just a placeholder. It could have been anything. It could also just be a value of c. And this gives us our first lesson about differential equations. Often there is not one solution to a differential equation. There is an infinite family of solutions. For every value of c, we're going to get a different solution. So how could you find the values of c? You actually need a little bit more information. So I want to redo the problem. I want to stay with the same solution that I had to that differential equation, but I'm going to additionally impose something called an initial condition. An initial condition is you telling me, well, how much quantity was there at time t equal to 0. In this case, I'm going to say I started with $1,000 at time t equal to 0, or there were 1,000 people infected at time t equal to 0, depending on what it is that I'm trying to model. And so with an initial condition, if I plug t equal to 0 into that equation, I just get 1,000 on the left is the constant times e to the 0. E to the 0 is 1, and that tells me that c was 1,000. And so my y of t is 1,000 times e to the 0.03t. I can go over to Desmos, the link to this is going to be down in the description, and plot what this looks like. This is just exponential growth. And so as time goes on, my value of my bank account, which begins at $1,000, is going to grow and grow and grow at this 3% compounded continuously. Okay, so that was one example of a differential equation. I want to leave you with a second. And in this second example, I'm going to imagine I start with a ball. I take the ball, I throw it straight up, and it falls down to the ground. So the idea was it was just moving vertically, but I had a starting spot, I had an initial velocity I gave it, and then it went up and back down until it hit the ground. Now, if you remember any of your high school physics, what we have is that there's a single force applied to this particular ball. I'm going to ignore air friction and all that kind of stuff. There's going to be a force of gravity, which is negative m times g. The negative is because my position, my y here, is defined to be positive going up, and the force of gravity points down. And then it's the mass of the ball times g, the constant acceleration of gravity in the surface of the Earth, 9.8 meters per second squared. Okay, so where's the differential equation? Well, it comes to us from Newton's second law, F equals mass times acceleration. The sum of the forces equaling the mass times the acceleration. So in this case, what is mass times acceleration? Acceleration is the second derivative of the position function. So I'll write it this way. The negative mg that we saw before, that's the only force on it, is equal to m times the second derivative of y. The acceleration is the second derivative of the position function, y of t. This, again, is a differential equation. Now I've got a second derivative in my equation. The m's on both sides, so they cancel, so it's just y double prime is a constant, negative g. Now, this differential equation is one that I can solve. I can find the solution just by integrating it. It's a second derivative equal to a constant. So let's integrate both sides. On the left, the negative g turns to a negative gt, and then I add a plus c because I'm doing an indefinite integral, and indefinite integrals give you plus c's. And then on the right-hand side, the y double prime turns into a y prime when you integrate once. I'm going to integrate a second time. The negative gt turns into a negative gt squared over 2 when you integrate once. The c integrates to a ct, and then because I'm doing a second integration, I get a second constant of integration, plus d. And then on the right-hand side, the y prime turns into a y. So what I have here is just a solution to this differential equation. It's a quadratic. And so as time goes on, the ball is going to go up and go down in this quadratic behavior. Indeed, this is one of the kinematic equations that you likely have seen before. What we've just done is to interpret it in terms of specifically a differential equation. Now, like the exponential growth example, this has two constants, a c and a d in it. So how do I find the c and the d? And if you imagine when I started with this ball, well, the path of the ball would depend on where my initial location that I threw it from was. That would change the path of the ball. And it would also change the path of the ball whether I gave just a little bit of velocity to it, barely threw it up, or whatever I gave it a much higher amount. That would affect the path of the ball. So those initial conditions, the initial velocity and the initial position, are going to be relevant. I'm going to state them. I'll say my initial position at y equal to 0 is y naught. It's just a constant. And y prime is going to be at t equal to 0, v naught. So y naught and v naught are two constants. And if I plug t equal to 0 into this equation, you just get d is equal to y naught. Likewise, if I plug 0 into the derivative of that equation, I'm just going to get that the c is equal to v naught. This leaves me my final solution to my differential equation with the specific choices of the initial velocity and the initial position specified. By the way, it's going to be very relevant to us in the future that in our first example of exponential growth, we had one derivative which gave one constant and we had one initial condition to specify it. But in this second example, we had a second derivative, y double prime, which gave us two constants of integration, and we needed two initial conditions to specify them. There's going to be a lot of theory wrapped around when exactly all this is going to work out. So let's leave with a few different questions. First of all, when do we actually have solutions to differential equations? If you write some differential equation, some equation with a bunch of derivatives in it, when do they actually have solutions? If they have a solution, is it one or is there many different solutions? I argued that there were some today, but maybe those equations have more, and that's also something we're going to have to really investigate the theory about. And then also, how do you find solutions? In the first example, I just asserted it to you. In the second, we could compute it, but very often, we're going to have to learn a whole bunch of procedures which says, given a differential equation, this is how we're going to try and solve it. So all that and more coming up in the future videos.